what's going on up here? Do you remember doing anything like this or seeing anything like this? They're called flame tests.
Just on the cover of a Gen Chem.
Yeah, cover Gen Chem book. They took a little wire loop like this, right? And they dipped it in solutions of different what? Different metals, copper, chromium, whatever, and they put it in the flame, and they saw different colors. What does that have to do with what we're talking about today? Can you imagine? You can identify different metals by their color, right? So that's kind of the start of atomic absorption spectroscopy, because that's the idea. It's trying to identify and quantify things. Although it's a little very different. But at room temperature, in a dilute solution of sodium and chloride, the sodium and chloride ions are in their what state?
Sorry, ground.
In their ground state, right? Okay. Ground state. So let's just go around and read these and tell me your answer. Kevin, we'll start with you in the back there. This first one. Why? Because of sodium, yeah, but all right, add some salt to water. Said all of these atoms are supposed to be in their what state in here? Ground state. Okay. Let's see here. I think I hear something there. There it goes. All right. Might be a bad spot to sit with what I'm going to be doing here, but it's okay. All right, so if I don't put anything, if I don't dip it, well, let's just dip it first. So dip it in there, get a little bit of the liquid on the little loop. I don't know if you can see it, but you put it in the flame. All right. So you're supposed to really get the flame hot really first, so that when you put it in there, you don't see any color. But sodium is everywhere, so you have to leave it in there for quite a while before you don't see any orange. Well, after you leave it in there for a while and you don't see any orange anymore, then you can get a little bit of your sodium solution. You put it in there. I should have brought one that actually had some color to it, right? But there it went pretty good. So why did it turn orange, Kevin? What did you say? Absorb or emit is the word we should be using here. Emit. Sodium's emitting orange.
So it absorbs everything else.
All we're saying is that sodium is emitting this orange light, right? That's all you can assume from this observation. Sodium emits orange light. Now, the sodium atoms that are emitting the orange light, were they in their ground state? No, they had to be in their excited state. So we're not saying, by this demonstration, we're not saying at all that all of them are in their excited state. But some of them did. And it's actually very, 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 very few. Because it's just that your eye is so sensitive. Your eye is like a photomultiplier tube. You're detecting individual photons. So you're detecting the emission from individual sodium atoms. That's how sensitive your eye is. But we'll talk about that more later, I guess. Oh, Bradley, why do atoms in a hot gaseous medium produce line spectra? Have we ever seen that before?
Emission?
Yeah, it's emission. So that's what this spectroscope is for. Okay, what you're going to do is in the front of this, there's a little slit. Okay, and let's start out with something that kind of makes sense, the sunlight. So you want to line up the little slit with the sunlight and then look through this end. Okay? So pretty much see the slit,
Rainbow.
right? But it's a really smooth rainbow. You see the really smooth rainbow? Right? It's Roy G. Biv like a smear. Okay, do you see that? Now do the same thing with the fluorescent lighting. Does it look the same?
They're narrow,
Yeah, I mean, you see,
and they've got gap between.
you have some gap, but you see all the major colors there, right? So you're just seeing white light here, but it's not natural lighting, okay? So if we try the same thing now with, whoa, which is it? I can only get it much darker. I can't get it much darker at all. This is kind of tricky because it's not that bright in here. But let's try the same thing with this guy. Hot gaseous medium. There's mercury atoms in here. So you have to, the trick is you got to line the slit up with the lamp. Where the heck is the lamp at? There it is.
Sorry, Mr. Higgins,
All right.
move a little bit to your left.
All right. Now, in order for you to see the right thing, you need to see that lamp.
Purple, green, and red.
But they're little tiny individual colors. It's not a broad thing at all. It's going to be looking like one of these, but not near as many lines. Your eye isn't near that sensitive. You're going to see some lines here, okay? That's going to look like this, is what you're going to be seeing, okay? So why do they produce line spectra? Are they absorbing or emitting? Emitting, right? So they're emitting light. And why? Because, well, energy is quantized, right? They can only have certain energy states, these electrons in those mercury atoms. Okay.
Because they're emitting quantized energy.
Yeah. So the quantized energy of the mercury atom is going to be different than the quantized energies of, pick a different metal. Right? Argon. It might look the same to your eye, but if you, through the spectroscope, you'd see a little bit of a different color. All right. Now you should see some different lines. Well, that was a really different color. See, what this really needs to be done in a black room, because you're getting light from behind it and things. We probably should have gone into that really dark room,
Yeah, the green
okay,
and
to do this justice. So we'll do that if we have room. If the hour doesn't end, right? If we don't use up the whole hour, we'll walk over there to that really dark room. Then you can see it. The atomic line widths. I'm Eustacio. How would you draw the absorption spectrum of a solution containing molecules? Right. I'll give you the axis. Absorbent. Whoop. That should be an A for absorbance. And a little lambda for wavelengths. What would you draw? Yeah, like a big blob, a little wavy thing. He's doing this with his finger, right? Okay. Absorption spectrum of a gaseous atom. So it has to be the same axes, absorbance and wavelength. But what changes, Shelby? Same thing? Yeah, it's not a blob anymore. It's going to be really sharp, right? It's pretty much going to look like this stuff, right? It's going to be really sharp. But it's not quite a line. You're supposed to, well, draw a line, but at the bottom you kind of draw a little width there, is what you should be drawing. Right? That there's actually width to it. There's actually some width to it, that it's not really a line. That, I guess it might maybe look more like that. But I'm trying to say that it's not an individual wavelength. There's actually a range of wavelengths, even though there should be just one, because it's going from this energy state to that energy state. You don't have all these solvent effects and all this smearing of energy going on. You have all these conglomeration. This is just a mess. But up here you just have gaseous atoms. So they should be aligned, but they're not quite. And the reason why they're not quite aligned is these three things. Now Bradley knows all about the Heisenberg uncertainty principle. Right? Pretty much this is the first one. This is PChem. The reason why that these lines aren't lines, or they actually have some width to them, the first idea is the Heisenberg uncertainty principle. That even if you went to absolute zero, you really don't know what the exact energy is. There's always some uncertainty in these measurements. And the more you narrow down, for example, position, the less you know about energy. Or the more you narrow down energy, the less you know about position. So it's quantum mechanics, and everything deals with probability at the very small microscopic level. So, and it's more of a PChem issue, but that's the idea. It's just nature adds statistics and uncertainty to it. Intrinsic. Doppler broadening. You ever hear of Doppler broadening? No?
I'm sorry, how did you define this principle broadening?
I would say it's just an intrinsic property of nature that you just can't narrow down the energy of anything, right? Even an electron that's excited and emits some energy, you can't narrow down pinpoint the exact energy. It's a limitation of nature. Nature won't allow it. And the more you try narrowing down certain measurements, the less you know about other measurements. So it's a peculiar system that you really can't relate to. It's like saying, I'm going to play catch with Eric and toss him a baseball. If it's an electron, Eric catches it. All he knows is it arrived, but we have no idea how it got there. That's one possibility. The other possibility is, he knows how he caught it, right? Maybe the energy to it, but then he knows even less about the path that it took or its trajectory. So Doppler broadening, make this as nauseating as possible. Okay. This is exactly 6.78 kilohertz, and you can hear it. It's a wave nature. Doppler broadening is a wave issue, and is light a wave? Yeah. So sound will have the Doppler effect because it's a wave nature. So will light. So if you're the detector, the emitter could be going towards you or away from you. I don't hear the same tone anymore. In fact, I hear more than one, don't you? It's going away from you, and when it's going towards you, the frequency is actually a little bit higher in pitch. When it's going away from you, it's a little bit lower in pitch. So likewise with there it is. Likewise with light, right? And you're trying to detect it. That little emitter could be traveling away from you. When it emits that light and you detect it, it's going to be redshifted. If the emitter is traveling towards you when it emits, it's going to be blue shifted. Okay.
They do with stars, right? Look up there and they're like one's blue, one's red.
That's
Distance.
That's temperature. So this is called the Doppler effect.
So if
Doppler
it's
broadening.
towards you,
So, and that's just, right, you can't stop these things. So that's just, again, another intrinsic property of nature that you're going to have this shift, this observed frequency. It's incorrect. It's because of the emitter that was traveling either towards you or away from you. So these atoms that are emitting light, pick sodium. They're emitting light. Well, some could be traveling away from the detector or towards the detector, so that's changing the wavelength a little bit.
so is broadening only if moving away from you and it's narrowing it? Like is
No,
Doppler
no,
narrowing?
no, because look, in the very center might be the true answer, but if you go a little bit longer wavelength, that's redshifting, right? Lower energy. So that would be a particle that's traveling away from the detector. The ones on this side, they're contributing to those wavelengths, those widths. Detector's going, right? The particle's traveling towards the detector. So there's just it should be one wavelength that's being emitted. It's sodium. but it's actually a little bit of a range. There's some width to it. There's some bandwidth. Okay? So when you saw the lines in here, they weren't perfectly individual lines. I mean, they look like they were, but they're really not. There's actually some width to them for these three reasons. The third reason is pressure broadening. If you want to get these nice sharp lines from these tubes that are filled with gaseous mercury atoms, for example, you want the pressure to be really low. If the pressure is really low, you don't get these weird effects of, for example, one mercury atom emitting light, then another mercury atom absorbing it, right? Or mercury atoms sitting there colliding with one another to try to adjust their energy levels a little bit. Okay, so you remove all these effects of pressure broadening. They kind of group all that stuff together and just make things behave, make the pressure really, really low. So that helps, but so it's probably a minor effect if you're doing it right. But it's the third component, pressure broadening. Pressure broadening is, I would say the biggest effect is with the pressures. Imagine it being really, really high. So we're supposed to have these energy levels, but they're more like, they might go up or down a little tiny bit if there's a collision. So that's one effect. The other effect might be something like quenching, where, yeah, one guy emits the light, but then you have another mercury atom that absorbs it before this keeps happening. Okay. Does that help? Okay, I don't know who we're picking on. Adrian, go ahead and, well, I guess you got a lot to read. And just tell us what you think. Yeah, fact. Yep.
Works in a very large population of atoms in the ground state and back at temperature of 99.9% of atoms are in the ground state. Atomic emission spectroscopy.
Yeah.
Works with a small portion, only 0.017% of the atoms are in their excited state of the flame.
So, which method, Adrian, do you think is the most sensitive technique for quantitating metals? Atomic emission or atomic absorption? With absorption, you got 99.9% of the atoms in their ground state. Right? 'Cause isn't that where you have to start? Because they have to absorb. With emission, they have to be in their excited state, otherwise you can't see them. Only 0.017% are there. It would appear that absorption should be the most sensitive. Does everybody agree? Just looking at those numbers. But is that the right answer? Yeah, it's not the right answer. Okay. But yeah, let's see if I can explain it to you why. Okay, first let's try a couple things here. One is absorption. So you are the PMT, right? You're the photomultiplier tube in the UV vis. This is the light source. So this is striking you, right? 'Cause this is a light source. This is striking your eyeball. Fine. Okay, now I'm going to introduce a little sample in the cuvette. Okay, and to get an absorbance reading, you need to measure the incident intensity and the transmitted. So this is the incident right now, right? So now you put your sample in, and you get this. Okay, now you can detect the change. Right? If you couldn't, you wouldn't be a very good UV vis. But recognize the difference. They're both still pretty bright, all right? But you can see it. Okay, emission spectroscopy. This room needs to be black, but I can't get it any blacker than this, right? Because that's what emission is. It's nothing there. There's no light source, right? It's black. So this is it. This is your background, okay? And then you get a little tiny light. It would work a lot better if this room was really black, because your eyes would be used to it. But you can see that. It's a much smaller population, but it's so much easier to detect changes. It's so much easier to detect intensity because there's no background. It's totally black. So emission will always win over absorption spectroscopy, just because of that background. Just because, so it's always, emission will always win because there's no background intensity. Right? You don't need to measure incident and transmitted. No. You're just measuring whether you detect light or not. Oh, well, okay, well, let's back up. This isn't atomic emission spectroscopy. This is atomic absorption spectroscopy. Well, then what the heck? Eric, why do we have a flame? Close. You're close. It's very close. But if we're going to analyze, I don't know, iron in beer. I guess they don't like iron in beer. I used to have that as a lab, but it really messed up the AA. It made it, everything all fermenting in here. It was disgusting. I had to clean it out. So it was a cool lab, but it was just disgusting. So, but iron in beer is bad. So if you're going to use, there's not much else you can use. You use the AA to analyze iron in beer. Well, you have to analyze iron. Iron will have a different absorption spectrum, will absorb different light than an iron ion. Iron plus 2 will absorb different than iron plus 1, which iron plus, whatever the oxidation state is, iron plus 3, right? So it has to be iron atoms. If you don't have iron atoms, you're not going to, it's not going to absorb iron light. Because in the lamp, you can have this iron light source. It has iron in it, emitting iron light. Only iron atoms can absorb it. So the only reason for the flame is to make atoms, atomizer, right? Because you can't have dissolved aqueous iron. It can't be ionized. You just need iron, gaseous iron atoms. So that goes for any metal you're going to analyze using AAS. You need atoms, and that's the sole purpose of the flame is to atomize things. Okay. So how does our AA introduce the sample into the flame? Well, here it is. This big nebulizer assembly. Now what part, Kevin, you done the AA? Yeah, now where's this little tube on here that you stick into the sample container? Yeah, here it is, that sample capillary. That's that little white Teflon tube that you stick into your sample. Okay. So what? There aren't any pumps or anything in here. What is causing it to suck up your solution, your sample up through that? There's a lot of acetylene, and there's a lot of an oxidant. You have air, right? That's coming in. That's, I guess, your fuel, your oxidant. Acetylene's your fuel coming in. All that stuff is coming in really close. There's a hint. It's coming in really close to this sample capillary. Right? When you So what is the path of the gas? The path of the gas is coming in through those tubes, coming in through here, and up there, right? That's the path of the gas. The path of your sample, somehow it's getting sucked up through here. Then once it's sucked up, well, then it's just carried through, right? And once it's sucked up, there's a little bead in here that's vibrating ultrasonic to make a mist. So you have this globules of droplets of your sample, and these baffles are there just to, only the finest mist can get through. So most of this stuff just ends up going to waste, just drips down and goes to waste. But we still haven't answered the question, why does this stuff get sucked up in the first place? The Bernoulli effect. Okay, it's the same reason why airplanes can fly. If this doesn't work, every airplane in the sky is going to fall out right now.
High pressure on the bottom, low pressure on the top.
So it's pretty much what has to happen, right? This is supposed to be an airplane wing. And if it's going to be elevated, fly or just stay above the ground, it has to have high pressure where? On the bottom and low pressure on top. If that's not created, it's not going to work. Exactly the same thing that has to be created here. It has to be high pressure out here, low pressure in here, so that it will actually get sucked up. But how does it create that low pressure? Same way a wing does, right? What's the shape of a wing? If you look at the side of the wing,
Curved wedge.
yeah, kind of like this, right? I'm sure it's more aerodynamic than that, but this is the idea. Flat on the bottom, curved on top. So the plane's flying. Let's say it's going this way. Does the air travel with the wing, or does the wing travel through the air? The wing has to go through the air. If it didn't go through the air, all the air in San Antonio would have to travel with the plane to go to Austin. That isn't going to happen, right? Planes travel through the air. So this wing is traveling through the air. The air has two possibilities here. It can either go where or where? Yeah, on top or on the bottom. Two paths, path A and path B. Which one does the air have to be moving faster? What? Now the plane is only traveling at one speed. Now the plane's only traveling at one speed. So does it make sense that one could be traveling faster than the other one? But look at the air on top. They both, since the plane is traveling at the same speed, both path A and path B, they have to reach the end at the same time. They have to reach the end at the same time. But because the plane's traveling at a certain speed, so whether you're in path A or path B, you got to reach the end at the same time. But which path, A or B, has a longer distance to cover? A has a longer distance to cover. So A has to be going faster. All right, faster moving air is a lower pressure. That's the Bernoulli effect. Faster moving air is a lower pressure. So what I can do is, if I blew air on this cardboard that's just, perpendicular, well, parallel to this board, right? Have air moving. I don't have the air moving down here. It has to be lower pressure on top. This thing has to float. For me to do that, all I'm going to do is just blow as hard as I can through this little tube. So you'd think that by me blowing on it, I should be blowing this little cardboard thing down here. I should. But look at the path of the air. It's going to go parallel to that board. That means lower pressure. That's air moving along a surface. That's lower pressure. Not moving down here. This thing should stick up to it. And the harder I blow on this, the more the more weight I could put on that. Right? So that's the Bernoulli effect. So with the Bernoulli effect, how is the Bernoulli effect being created here?
Pressurized air is blowing faster through.
Pressurized air is blowing directly across the little nozzle. It's blowing, here's the nozzle, it's blowing directly across. I'm sure they don't have the little nozzle set up pointing out this way or anything. They want that air blowing directly across. See how they're even coming in perpendicular? They want it blowing directly across that opening so that you just have lower pressure. No, it'll get sucked up. Atmospheric pressure is pushing it up because the atmospheric pressure is higher up here.
So in theory, we should be able to blow that on it really fast and still get something to suck up.
You should be able to what?
We should be able to blow across on that fuel line or that auxiliary oxidant line. and
Oh, yeah. Yeah.
still get stuff to
Yeah.
blow on.
Yeah. Except the flame will go out. Okay. The last idea here, I don't know. I guess, you should have the right to know when you're using these machines, but this thing could kill you. It could explode.
That's awesome.
It could explode. Now but you could get you could fall down the stairs, you could get electrocuted pushing a keyboard, if things get messed up, right? So there's a lot of safety factors on this thing. So I wouldn't be so comfortable using a really old instrument because all those safety factors aren't around. But what could happen here? What could happen here is, look at all this fuel and air. It's all blowing through here, right? And it's all contained. Doesn't sound like a good place to be for a flame, because you have a flame right up here. What if that flame crept down? Doesn't need to creep down too far. Things ignite in here, you're going to have an explosion. And that's a flashback. So that idea of velocity, you can kind of see it here. We talked about velocity of gases and their preferred.
So that's why we turn the gas on first and last, right?
Right? If I have things really messed up, see how the flame is going lower and lower and lower? I can get it to stay ignited inside the tube there. So that's not the appropriate velocity for these gases, for this gas mixture. So things could get screwed up, and it could happen. But that's why they have all these safety features here, relief vents and all that. There's nothing. Yeah, I think you'd just hear boom, and you'd crap your pants, and then everything's fine. So that's about it.